last class, the bonus lecture, that's not really a bonus lecture but is integral to the class, we learned about the ideal gas law, which is this PV equals nRT that you see on the left side of the screen. PV equals nRT. This is our ideal gas law. This is the one that you should definitely memorize. Absolutely, definitely memorize it. P stands for pressure, V stands for volume, N is the number of moles, R is our ideal gas constant. That will always be given to you. It's often got these units, liters, atmospheres per mole Kelvin. There's another version that's on your yellow sheet that I think has different pressure units. That's basically the only unit that you'll see changed when you encounter it for gas calculations. There are other versions of R that have like what we would consider crazy units. We probably won't see those. And then T is temperature. And what unit does temperature need to be in? Kelvin. Temperature has to be in Kelvin. And one of the nice things about the R value here is the R value tells us what units we need to have for the related value or variable. So for example, we've got volume with liters. Liters matches what we've got in our R value, and so that means that we've got the correct units. We've got pressure in millimeters mercury, which does not match with our atmospheres, so we're going to have to convert that. And our degrees Celsius doesn't match with our Kelvin, so of course we're going to have to convert that. So you were already given a little bit of time to try to solve this. The best way to solve, or one of the ways that I like to solve these, is just write down all the variables over on the side just so that we've got them all nice and in one place and they're pulled out from the problem text. So our volume is 0.270 liters, our temperature 88 degrees Celsius, and we need to convert that to Kelvin. So we add 273.15 to get it into Kelvin, which is 361.15. We are also given pressure in units of mmHg, millimeters mercury. And we need those to be in atmospheres. Millimeters mercury is the same as torr. There are 760 of those units in 1 atmosphere. So we divide by 760 and we get something close to 1.28 atmospheres. Well, we are trying to find molar mass. What units does molar mass have? Usually, when we see it. Grams per mole. So we're looking for grams over moles. We have something it's not exactly grams, but we have milligrams, and we can turn that into grams. So it's 827 mg. That's our mass. I'm just going to write it in as 0.827 grams, what we would get if we converted to grams. So we've got the grams. We just do not have the moles. So we're going to need to find moles with our PV equals nRT. So we do some algebra, and N equals PV over RT. N is our number of moles. And then we can plug in for PV and RT, and we will get 0.01169 ... moles after we do that. Now we've got the moles that go into our molar mass, so we take the grams, we divide it by moles. That'll look something like this, 0.827 grams over our number of moles. And we get, after we round for 3 sig figs, 70.7 grams per mole for our molar mass. And then for some extra fun, we can maybe guess what gas this could be. What's got a molar mass that's around 70 that's a gas? This is harder than the one that we did in class last time. Could be chlorine. Chlorine's got a molar mass of 35.45, but it's Cl2. Cl2 would have a molar mass of 70.90, which is relatively close to what we've got here. It's just off by a couple percent. Questions about all that? Great. We can also mix gases together. So according to kinetic molecular theory, each of the components in a gas mixture acts independently of the others. So the identity of gases doesn't matter. In ideal situations, gas identity does not matter. All gases behave the same. This is not true for the real world, for real gases. It's close enough. We can just kind of approximate that it's ideal most of the time. So because the gas identity doesn't matter, it's just the total number of moles of gas that matters, we can use this fun little trick. So the pressure to any individual component in a gas mixture is called the partial pressure. The pressure contribution of one component or part of the mixture. And the partial pressure, since the identity doesn't matter, they all contribute equally based on the amount of moles that there are. The partial pressure of any component is its fractional composition. What fraction of the mixture is that gas? So that's the moles of gas over total moles. It's the percentage, but a fraction form. Like what percent of the mixture, but the fraction form. So you take that fractional composition, you multiply it by the total pressure of the mixture, and that gives you the partial pressure. I think we've got this written slightly differently. Fractional composition is percent composition divided by 100%. So for example, our air is roughly 78% nitrogen, 21% oxygen, 0.9% argon, a little bit of carbon dioxide, and some other things in even smaller amounts. So the nitrogen molecules, the N2 molecules in our air, exert 78% of the total pressure because they're 78% of the total molecules. It's independent of the presence of the other gases. Our oxygen molecules exhibit or exert about 21% of the total pressure. So this partial pressure we could also write as P sub anything. We'll call it A. Fractional composition is often using this chi letter from Greek. And then total pressure would be P sub TOT. That'd be our mathy way of writing it. So for the nitrogen and the oxygen, the partial pressure of the nitrogen is going to equal its fractional composition times the total pressure. We're at about 1 atmosphere of pressure. It's a little lower than that. And then the fractional composition is 78% divided by 100. So 0.78 times 1 atmosphere. So the partial pressure of nitrogen is about 0.78 atmospheres. If we were at higher elevation, the pressure would be even lower, significantly lower than 1 atmosphere, so it would be lower than 0.78 atmospheres, even though the fractional composition doesn't change. The optimist says the glass is half full. The pessimist says the glass is half empty. The chemist says the glass is 50% H2O as a liquid, 39% N2 as a gas, 10.5% O2 as a gas, and some argon and carbon dioxide in there too. It's full, it's just not all liquid. All right, example, a gas mixture contains 2 flammable gases, methane and ethane. It's 64% methane, 36% ethane. If the total pressure is 1.44 atmospheres, what are the partial pressures of each component? So again, the mathy way that we write out that partial pressure formula, the partial pressure of A is the fractional composition of A, that's percent divided by 100, times the total pressure. And you can rearrange this to your heart's content if you're solving for total pressure or fractional composition, what have you. So we're looking for partial pressures of each of our components, methane and ethane. I'm going to shorten methane to me and ethane to et. So our partial pressure of methane is equal to our fractional composition of methane. So we're going to take this 64% and divide it by 100. So it's 0.64. Multiply that by our total pressure of 1.44 atmospheres. And we get a value of 0.92 atmospheres. And then for PET, our partial pressure of ethane is 0.36 times 1.44 atmospheres. Our fractional composition times our total pressure. And this should be the rest of the total pressure. So 0.52 atmospheres. Generally, when you add up these partial pressures, it should add up to about the total pressure. It's sometimes going to be off by a little bit because of rounding, but it should add up to about 1.44 atmospheres in this case. Questions about our partials? I said partials and I had flashbacks to calculus. Okay, other stuff we can do with partial pressures. This is actually what I was talking about, where we add up the partial pressures. So Dalton has a law of partial pressures. Dalton's law of partial pressures says the sum of the partial pressures of each component in a gas mixture must equal the total pressure. So the total pressure is equal to the partial pressure of A plus the partial pressure of B and C, and then whatever else we might have. So however many components you have. So P sub A is the partial pressure of, it actually says this below, so I'm not going to rewrite it. But P sub A, B, and C are partial pressures of components A, B, and C. And you can add more terms if you need to. Usually we'll have 2 or 3. So it's not unnecessarily messy or long. All right, let's say that we have a sample of hydrogen gas and it's mixed with water vapor. The mixture has a total pressure of 734 torr. The water vapor has a partial pressure of 22.5 torr. Please find the partial pressure of the hydrogen gas. Okay, so we are going to be utilizing Dalton's law of partial pressures. We've got a mixture. It's hydrogen gas and water vapor. So it's water vapor, H2O, and H2. Those are the two gases that are in the mix. Just those two gases. So their partial pressures, the partial pressure of H2O plus the partial pressure of H2 must equal the total pressure. So the total pressure is equal to the partial pressure of the H2 plus the partial pressure of the H2O. That's why we have this first sentence. It's establishing we have only two things, so somebody can't, actually we might have more gases in there. No, it's just the two things. So the mixture has a total pressure of 734 torr. So P sub TOT, 734 torr. Water vapor has a partial pressure of 22.5 torr. So our P sub H2O equals 22.5 torr. Remember that torr is the same as mmHg. So taking our equation, our Dalton's law of partial pressures, we want to solve for the pH2O. Sorry, pH2. We have the H2O. So we need to subtract our pH2O from both sides. That turns this into P sub H2 equals the pressure total minus the pressure of H2O. So 734 torr minus 22.5 torr. And we'll get a value of 711.5 torr, and then we get to round that to the ones place, so 712 torr. Questions? Neato. Partial pressure also comes into play when you're going to really high elevations or when you're going down to the depths of the deepest, darkest bits of the ocean as well, if you're like scuba diving, for example. So our lungs perform best at an oxygen partial pressure of 0.21 atmospheres. We operate really well, we work really well at sea level. That's where we tend to breathe the easiest. If you go to higher elevations, the total pressure decreases because you're further up in the atmosphere, and so there's less air pushing down on the air that you're in. That's the reason why. And so the partial pressure of oxygen also decreases. So that's why if you go up to like really high elevation, if you try to go scale Mount Whitney or something, it tends to be a lot harder to breathe. You find yourself running out of breath more because there's less oxygen. And if that gets to a severe extent, then you can get hypoxia, hypo plus oxia, the oxia for oxygen, hypo for low or less than, which is oxygen starvation. And severe hypoxia, like people up at Everest, can result in death. So if you're summiting Everest, you're typically going to bring oxygen, and even then it's not super safe necessarily. So you'll just carry along a tank of oxygen so that you can supplement when you need it. You can also, though, have too much of a good thing. So oxygen toxicity occurs when the pressure of oxygen is above 1.4 atmospheres, which you're not going to get normally. But if you're scuba diving, the pressure of the water around you pushing on your lungs makes it really hard to breathe. If you've ever tried to take a pool noodle and you like just go a little bit under the water and you try to breathe through the pool noodle, it's so hard. It's really difficult. It's like impossible once you get even just a couple feet down because of the increased weight of the water pushing on your chest. And so to counteract that, when you go scuba diving, you breathe pressurized air so that the air basically forces your lungs to let you inhale against the pressure that's outside of you. So you have to increase the total pressure, which means that the partial pressure of oxygen can also get jacked up. And so you can get fun symptoms like twitching, tunnel vision, convulsions, things that normally go along with a good time, right? A bad time. There's also the possibility of getting an increased partial pressure of nitrogen if you're just breathing pressurized air, and you can get this very fun nitrogen narcosis. Narcosis like sleeping. This is also called rapture of the deep, which sounds way cooler, and apparently is fairly similar to being tipsy. So maybe a good time. If you're a deep sea diver, if you're going below 50 meters, 150 feet-ish, 165 feet, something like that, then you're probably going to be using a specialized mix like Heliox. Heliox is a mixture of helium and oxygen, helium like in party balloons. So I bet if you talked, it'd sound really funny. But also the helium's not going to go into your bloodstream and screw you up like the nitrogen would. And then you can just adjust the amount of oxygen that you get to avoid that nitrogen narcosis. We'll have some problems where that becomes relevant. Okay, to the example that we did before, when gas is collected through water, we've got an upside down beaker full of water here, and we pipe in some gas. The gas is all going to float up to the top, and that's going to push some of the water out. So that's a way that we can collect the gas without air getting in. But when you do this, there's also water vapor that's coming up. So a little bit of that water is going to be coming up and turning into vapor. And so the mixture of gases in here is going to be the gas that we're collecting, but there's also going to be water molecules mixed in there. So there's going to be a little bit of water vapor in there, and that's why we need that law of partial pressures. I believe we'll be doing this in at least one lab. And the pressure of the water depends on the temperature that the gas is collected. So you'd refer to a table. Refer to a table for vapor pressure of water. Vapor pressure is slightly different from partial pressure. In this case, they're the same thing. And then the rest of it will be the gas that we care about. So here's an example of doing that sort of a problem. So we do a reaction and we get hydrogen gas collected over water. The total pressure is 758 millimeters mercury. So our P sub TOT, 758 mmHg. That total pressure is just whatever the atmospheric pressure is, because the pressure inside of our little container, inside of our upside down beaker, is only going to push water out to the extent that it's balancing with the pressure outside. So the pressure inside our container is going to equal the pressure outside of our container. Since it's not sealed or anything, the water can move out. And then our temperature is 25 degrees Celsius. And we want to know what's the partial pressure of the hydrogen gas. So we would refer to a table that looks something like this, probably with a little bit more granularity, smaller increments between our degrees Celsius. So a temperature of 25 degrees Celsius, we find that on our table. And that means that our vapor pressure of water is 23.76 millimeters mercury. So our P sub H2O, 23.76 mmHg. Then we're going to use our law of partial pressures. Thank you, Dalton. We've got our pressure of H2O and our pressure of H2. We want the H2 by itself, so we subtract the PH2O from both sides. So P sub H2 is our total pressure minus the pressure of water. We round to the ones place, 734 mmHg. Questions? Cool. We can also do stoichiometry with this. So in reactions that involve gaseous reactants or products, the amount of gas is often specified in terms of volume at a given temperature and pressure instead of mass. Have you ever tried to take a gas and set it on a scale and weigh it? No, because you're not crazy, right? Like, you're not gonna, oop, that's a weird smell. Let's put that on the scale and see how much that weighs. Practically, it doesn't make sense to do that. It's a lot easier to measure a volume and temperature and pressure. You could do it if you trapped it in a balloon and you knew the volume, the mass of the balloon, and then you knew the mass on the scale. Like, you could do it, but it's not reasonable to do it most of the time. So, with volume, temperature, and pressure, we can use the ideal gas law. Who remembers the ideal gas law? Nobody remembers the ideal gas law. We're shy, that's okay. PV equals nRT. So we can convert pressure, volume, and temperature to moles. So we're solving for N. We're going to divide by RT. Flip the left and the right sides. N equals PV over RT. So this finds the moles of gas. And then once we've got moles of gas, we can use stoichiometry. We can use the ratio from our balanced chemical equation. To convert to other chemicals. And this could be going to another gas, and then we could be solving for the volume of that gas or the pressure of that gas. It could be going to a solid, and so then we'd be converting then to grams at the end. We'll learn later that there's other things that we can do as well. But let's do an example. So sulfuric acid is the industrial chemical produced in the greatest quantity in the United States. It's prepared by this overall chemical reaction. Sulfuric acid is used for all kinds of stuff. One of its uses is for acidifying blueberry fields. And I think they also use it for clearing drip lines, so you don't get hard water deposits. So this is our balanced chemical equation. What volume of O2 in liters at given temperature and pressure is required to produce this large amount, 907.18 kilograms, of sulfuric acid? What are we finding? This is a type of question where it feels like it's worded backwards. So that's part of why I'm asking. What are we looking for? We're looking for volume of O2. So we're finding liters of O2. What are some things that we are given? What's maybe a place that we could start? We were given temperature. We were given pressure. So we've got pressure and temperature. We're looking for liters. What's an equation that we might use that involves those three things? Yerp. It's the ideal gas law, PV equals nRT. So if we're finding liters, liters is volume, so we'd be using V equals nRT over P. And we've got temperature, and we've got pressure, and R is a constant. Do we have N? N is the moles of O2. We do not have N, so we need N to be able to get to liters of O2. So we need moles of O2. Moles being the symbol N in our ideal gas law. How can we get to moles of O2? We've got O2 in our equation. How can we get to it? What would we need to be able to get to moles of O2? We're going to use stoichiometry, yes. What's a chemical that we have something for? Because we would need sulfur, H2O, or H2SO4, moles of that to get to moles of O2. Which one do we have? Just H2SO4. Right, we were given an amount, kilograms of H2SO4. So from moles of H2SO4, since our balanced chemical reactions, these are always moles to moles. So we must have had moles of H2SO4. Do we have moles of H2SO4? Unfortunately, no, we do not have moles of H2SO4. Do we have something that can get us to moles of H2SO4? We could get there with mass. Grams of sulfuric acid. So if we convert our kilograms to grams of H2SO4, we can use our grams to get to moles. What do we need to go from grams to moles? Or moles to grams. Grams to moles to moles to grams. What do we need? Molar mass. Do we have molar mass? We do not have molar mass. Can we calculate molar mass? Hopefully we can calculate molar mass. We can. So we've got two hydrogens with 1.008 grams per mole each. We've got one sulfur, 32.066 grams per mole. We've got four oxygens with about 16 grams per mole each. We add all of those up. So we do 2 times 1.008 plus 32 and change plus 4 times 15.999. we've got a molar mass of 98.078 grams per mole. We have all the tools we need. We can solve the problem. I would like to take a moment to point out, I thought about saying I told you so, but some concepts that we hadn't thought about in a while, like calculating molar mass, right? That's come back. We're going to still continue to need that. Stoichiometry has come back. We're going to continue to need that. The new part of this is the PV equals nRT bit at the end. We will keep using stoichiometry, our ratio from our balanced equation. We will keep using molar mass. So if you haven't done those in a while, if you're not sure, if you're not 100% confident how to do those, guess what? You can go to Logan's SI sessions. He'd be happy to go over them with you. Or come to my office hours. I'm so lonely in my office hours. It's incredibly boring. Please come make my life more interesting. My 2 Costco-sized bag of high chews are just desperately lonely, and they need some company. I do also bring them to SI sessions sometimes, yes. Okay, so starting with our grams of sulfuric acid, we're going to divide by our molar mass, because then the grams go on the bottom, the moles go on the top, grams cancel. We're going to use our ratio. We have H2SO4. So on the bottom, 2 moles H2SO4. That gets formed from 3 moles of O2. Can you imagine if we added a limiting reactant part to this? Ooh, that'd be fun. Just reminding you that that's also a concept. Okay, so moles H2SO4 we cancel out. Now we've got moles of O2. Moles of O2 is the N that we need in our V equals nRT over P. I'll pause the calculation there, just so we get a little number to look at. It's a very large number for what we usually see. It's 13,000 moles of O2 and some change, of course. And then we get to plug this into V equals nRT over P. Of course, our pressure is not in the right units. Who did this? So divide by 760 to get it into atmosphere, 0.980 atmospheres. And our temperature is also not correct. So add 273.15 to get it into Kelvin, and it's 295.15 Kelvin. This is like the most complicated that I could have made this, by the way. Okay, so V equals nRT over P. We've got everything we need. We've got the pressure, we've got the T, we've got the N, and R, of course, is given to us. And now we get to write all of the numbers in. So 13,874.3 ... moles O2 times R, liters atmospheres per mole Kelvin, times temperature, 295 Kelvin. Kelvin and moles cancel. On the bottom, we've got pressure. In a classic turn of events, I've completely run out of space. This happens all the time to me, by the way, every semester. Okay, so this is the mess that we're putting into our calculator. And after all that, we get a whopping 342,970,2019 liters of O2. We would round that to 343,000 liters of O2, which is a lot of oxygen. I have no concept for how much oxygen that is.
Where's your scientific notation?
Here it is. Oh, got to write the correct numbers. 3.43 times 10 to the 5 liters O2. And that's probably what you would see as the answer. Again, about as complicated as it could possibly be. Numbers bigger than we would normally see. Questions about any of those parts, revisiting all those topics. Cool. There is also a set of conditions that we call standard. Standard temperature and pressure, also known as STP, is 0 degrees Celsius. What is special about 0 degrees Celsius? What happens at 0 degrees Celsius? My teeth shiver and they clack against each other and I get the little icicles forming out of my nose like I'm Patrick. It's the freezing point of water. So that's one of our standard conditions. That's standard temperature. Our standard pressure is 1 atmosphere. What's special about 1 atmosphere? Where do we experience 1 atmosphere of pressure? In an exam? Might feel like an atmosphere of pressure. Sea level. If we're at sea level, that probably means that we are at the sea, at the beach. Usually a good thing. So we're freezing cold, not a good thing, but we are at the beach. So that's STP. So 0 degrees Celsius is a very convenient number to memorize. 1 atmosphere of pressure, a very convenient number to memorize. At STP, 1 mole of gas, you can do this. I'm running out of battery. Me being my iPad. Plug in for 1 mole of gas with 273 Kelvin and 1 atmosphere. What's the volume? It turns out it's 22.4 liters per mole. This is the volume of gas at STP. Volume of a gas at STP. It only works for gases. It only works at STP. Only works for gases. Only works at STP. Please never use it for anything else. I'm saying please never use it for anything else because I see people use it for solutions, which are not at STP and are not gases. Don't use it for those. iPad has fallen. We had 1 slide left. Pause real quick. I'm just going to stop the recording and then you can ask me about it, I guess.